Hello, my name is Daniel Sepos. I am a director of analytics at a large property and casualty insurance company. And in this video, I will discuss a final project for the Machine Learning Foundations for Product Managers course, part of the AI for Product Managers uh, specialization provided by Duke University in Coursera. So in this video, I will discuss the final project of this first course. And in this project, we were asked to take a sample data set and create two models based on the sample data set, compare those models to find a superior model. I did this in Excel, and I'll walk you through the steps I took at this point. The first step was downloading all of the raw data from the website, and in this raw data, what we see here is four different feature variables: temperature, exhaust vacuum, ambient pressure, and relative humidity, as well as a fifth target variable here called energy output. The model that I decided to do here was a multivariate regression model in Excel using the Excel data analysis plugin here. So the very first step I took was identifying my training set, validation set, and test data set. So I used a random number generator to identify 80% of the total observations here, nearly 10,000, to appear in the training data set, about 10% in the validation set, and about 10% in the test data set. And what I'll do is I will run a regression model on the training data set first to find a model. Then I will run against the validation set, identify a change I'd like to make to the model, then run a second model based on that change data set, the training set, compared to the validation set. And then after selecting a model, I'll run the test data set against it to see how it performs. So for the first model, what I decided to do is a simple regression, taking each of these four target variables, trying to identify the relationship to each of these four feature variables and trying to identify the relationship to the target variable, which is energy output. After running the analysis, we see that the model, based on the R-square, the model appears to have a fairly good fit here. 92% of the variance in energy output can be attributed to each of these feature variables in here, which is good. There's a statistical significance is well within the 5% margin there. So this is a statistically significant output based on the number of observations here. And as you can see, there are several, the intercept coefficient, which is the bias of the model, several coefficients associated with the feature variables as well, each of which does make change into the model here, the smallest of which is ambient pressure, which for my second model, I will take out ambient pressure and run the model again. Each of these outcomes is statistically significant, so that's good. And I took the residuals here, an absolute residuals, in order to run some error analysis there in the next sheet here. So what I did was I compared the validation set to the training set and ran error against it to see how that comparison would work. As you can see, the mean squared error is rather large, 18.7 here, which just means that this model is that's the impact of it's largely driven by the impact of outliers here. As you can see, the mean absolute error is similar for the validation set versus the training set, which is good, as is the mean absolute percentage error. So this is a pretty good model, all things told here. That said, as I mentioned a moment ago, ambient pressure offers the least impact to this model. So perhaps there could be benefit in taking out this particular feature to improve compute and perhaps interpretability on the model. So that's what I did in the second cut of this, in the second regression model. As you can see, the R-square is very similar in nature, also roughly 92%. We do see statistical significance and there are three feature variables for one target variable. The bias is a little bit different, however, it's a little larger in this case. And the temperature has changed, and other coefficients here have changed. So I then did perform the validation set against the model using the same validation set as the first model, and you can see the mean square error is a little larger. This tells me that the second model has a tougher time handling outliers than the first model. Although if you look at the mean absolute error and the mean absolute percent error, the difference is negligible between the two models, and it seems to be right on par with the training data set as well. So again, the second model is also a fairly good fit, although in the next sheet here, when I compare the two, you can see that the first model does have a slightly better fit here in terms of R square, meaning that the fit is a little bit better. As we saw before, the mean squared error for the first model compared to the second model is also a little bit better. And even though the number of features in the second model is smaller, 3 features versus 4, therefore it perhaps requires less compute and perhaps a little more interpretable. If you value those things, if you value compute, the second model could provide a good option. However, I chose the first model because it seemed to be negligible in nature there, and we were able to handle outliers slightly better. So running the test data on that model, you can see very similar here. The mean squared error is better on the test data set, which tells me that there may be fewer outliers in this set, just by virtue of being a random set. But the mean absolute error and the mean absolute percent error, they're right on par there with the validation set and the training set for the first model. So this tells me this is a pretty strong fit for both for the test set, the validation set, and on the training set for the first model. So I know this is a little bit over. Thank you for watching. This is my final project for this course in the specialization. Thank you very much.